So this is the pre-lab for the last in-person experiment. So if you guys remember from the schedule, we're only doing 4 in-person experiments this semester, and then after this experiment, there'll be 2 more experiments that are going to be done completely virtually. So this is going to be the last one you guys have to prepare for coming in lab. And for this experiment, we're doing titrations. So we're going to be titrating some vinegar. So I'm going to go over some the basic lab equipment you guys are going to use and then the chemistry behind it, and then you guys should be all set for this experiment. So because we're doing titrations, we have to very accurately measure volumes. So we're going to be using what's called a burette, which I have a picture of here. So you guys can see the burette reads from the top down. So the top here is 0, and then the bottom here would be 50. And basically what the burette lets us do is very accurately dispense a volume of solution. So you use this little valve down here to control it. You can get down to going drops in as opposed to, just letting it full open and stuff. And that's going to be very important for when we get close to what's called the endpoint. So you're always going to have 2 readings with a burette. You're going to have your volume initial and your volume final. So if you're not comfortable with this, you guys can always just fill this and start at 0. And that way your initial volume 0, so your final volume just tells you how much you dispense. But if you're comfortable with it, instead of refilling it every time, if you have enough in the burette, you can keep going as long as you keep track of this. So basically the way we find out how much volume we've dispensed is simple. It's just going to be our volume final minus volume initial. And that will equal the volume used. So why do we care about how much volume we use? Well, that has to do with us being able to figure out how much of something we had. So we kind of went over this last week with one of the stations, but we're going to be doing an acid-base titration. So if I had a generic acid, so if we just call it, in this case, HA, and I react it with a base, we'll call it generic base, we'll call it BOH, we're always going to get water, and we'll get a salt. In this case, it'll be generic AB. That's usually aqueous. This will be liquid. This is aqueous. And this is aqueous. So because this reaction is very efficient, it basically all completely reacts when we do it, we can use the equation here to figure out how much of something we have. As long as we know one of these, we can solve the other. And the way we do that is we're going to use the molar ratios here, but we're also going to use the concentration formula. So if you guys remember from Gen Chem lecture, our molarity is going to be equal, that's big M molarity, is equal to moles per liter. So if we have a known concentration, which we do, and we have a volume dispensed, which you guys will measure from this, we can rearrange this and we can get molarity times liters is equal to moles. And again, we do have liters. Just remember, guys, the burette's going to measure in milliliters, so you got to do that conversion. And if anyone needs a reminder, there are 1,000 milliliters in 1 liter. So your conversion factor is 1 to 1,000. So if I had something like 25 mils, to convert that to liters, I want to cancel out the mils in this case. So if we're doing this dimensionally, the mils go down here. So 1,000 ml, 1 liter. And you guys can see something divided by itself is 1, so it cancels out. So the mils go, and I'm just left with 25 divided by 1,000. And that's just moving the decimal place 3 spots to the right. So 25 mils would be 0.025 liters. So very important, you guys are comfortable with conversions because you're going to be measuring in mils, you're going to need liters for this. So that's going to give us moles in this case. So you guys can see from the above reaction, if everything's 1 to 1 to 1, which in this lab it should be, the moles of base I use, which is what I'm titrating with, should equal the moles of acid that we have in solution. So what's this going to look like for us on this lab? So we are actually going to be titrating vinegar. And you guys may remember me earlier in the semester saying that vinegar is a solution of acetic acid. So we're actually going to be solving for that and seeing if you guys can measure the right ratio, because according to the FDA, vinegar has to be a certain percent by weight acetic acid. So we're doing a little quality control testing, really. So acetic acid is an organic acid, so it looks a little different, but it's not too scary. So what we have is CH3 COOH. So for those of you who don't know, organic acids have this group right here. And what we're looking at is the acidic hydrogen in this case is this guy here. So just like if I had, say, HCl, how this guy's the acidic hydrogen, this is the one that comes off. In acetic acid, it's just this last hydrogen that we denote, the one that comes after the COO. So this is our acetic acid that's going to be in our vinegar. So our whole goal is we want to know what the amount we have of this is. So we're going to use an acid-base reaction. So we're just going to react it with sodium hydroxide. And just like the generic equation above, this is going to give us water and a salt. So in this case, it would be sodium acetate. So we'd get NaCH3COO. So you guys can see, just like if I reacted HCl off and the Cl would be left over and I would get NaCl, in this case, this hydrogen comes off and I'm left with NaCH3COO. So this is what we know as sodium acetate. So the question is, how are we going to know when we get to the end point of this? There's a couple ways you can do it. The way we're going to do in the lab is we're going to use what's called an indicator. So an indicator is a chemical we use in a solution to tell us the pH. So it doesn't directly interact with this reaction, but it's going to kind of report back to us. It's going to indicate when we're at an endpoint. Now, every indicator has a different point in which it changes color. The indicator we're going to use, which is phenolphthalein, is perfect for measuring the endpoint of this because the color change is going to happen right in the range we want. So phenolphthalein goes from a clear color in acidic solutions to a bright pink in basic solutions. So the ideal endpoint that we want is going to be a very, very faint pink. It's going to almost look like it's colorless until you hold it up to the white of the back of the hood, and then you'll be able to see a very, very, very faint pink. That is the most ideal endpoint that we can get for this. If you guys go a little over, it's fine. Just know the measurement's going to be a little bit off. And you guys can see here, our equation is balanced. So everything is 1 to 1 to 1. So we don't have to really do a mole ratio when we do our calculations for this. Now, if we're dealing with a acid that had multiple hydrogens on it or a base that had multiple hydroxides, there would be a molar conversion we have to use because the ratio wouldn't be 1 to 1. But you guys can see by this reaction, 1 mole of acetic acid is going to react with 1 mole of sodium hydroxide. It's going to give us 1 mole of water and 1 mole of sodium acetate. So I'll kind of walk you guys through what the problem would look like. So again, we're going to be trying to solve the ultimate goal is we want to find out what the weight percent is. So percent weight of acetic acid. So this is our ultimate goal. So with chemistry problems, it always helps to kind of write out a game plan or have a game plan on how you get to your unknown from what you have. Let's say we had 2.4 grams of vinegar to start. Let's say we had 0.1 molar sodium hydroxide that we used to titrate, and it took us 22 milliliters to hit an endpoint. So this is all our givens. Always good to write your givens down, like I said. And we want to find the weight percent. So how am I going to get from a concentration and a volume all the way down to weight percent? So first thing I'm going to have to do is solve for how many moles of sodium hydroxide I have. So another given we have, kind of wrote it earlier, but molarity is equal to moles per liter. And moles, in this case, is going to be equal to grams over molecular weight. We're going to need that at the end to be able to get our weight percent, so good to keep this one in the back of your head. First thing, we have to rearrange this in order to solve for moles, because we have a concentration, we have a volume, so we have to get that in terms of moles. So molarity times liters will equal moles in this equation. So this is going to be moles of, always kind of important to keep track of what exactly you're solving for. If you're comfortable, you don't have to write that out, but if you're not, always good to keep straight what you're in. So this will give us moles of sodium hydroxide, because we're talking the concentration of sodium hydroxide, we're talking the volume of sodium hydroxide we dispense, so that's going to give us moles of sodium hydroxide. If we look back up at our equation, remember I said everything's 1 to 1 to 1, so we can say for every 1 mole of sodium hydroxide is equal to 1 mole of our acetic acid. And again, I'm just looking at the chemical equation for this. So if there are any coefficients in front of these, this molar ratio would change. It would be something like 1 to 2, 2 to 1, so on and so forth. But in this case, it's 1 to 1. So this calculation is fairly simple. Always get in the habit, guys, of writing this down, even if it's a 1 to 1 ratio. That way you don't forget it when it's not a 1 to 1 ratio. It's a very easy way to get a wrong answer on problems like this. So now we're going to be in moles of acetic acid. So now that we're in moles of acetic acid, I need grams because we want a weight percent. So if I look down here, moles is equal to grams over molecular weight. So if we reconfigure this, if we do moles times molecular weight, that will equal grams. And again, this would be acetic acid. Now that I'm in grams of acetic acid, we need a weight percent. So percent weight is going to equal grams of acetic acid, which we just calculated, over grams vinegar times 100. And that's it. Once we plug everything into that, we would get our percent weight. So now that I have everything written out, we can actually plug in the numbers. So another nice habit to get into, guys, is before you do any of the math behind it, any of the arithmetic where you're throwing the numbers in, try to get all the formulas you need done first. It's easier to rearrange things when they're just variables as opposed to numbers. You don't have to worry about losing numbers. This just gives you kind of the game plan that you need in order to do this. So now we can go through and calculate it. So remember, we got to convert this mils to liters for all this to work. So we have 22 milliliters, and we want to convert that to liters. So again, for every 1 liter, we have 1,000 milliliters. Milliliters cancel out. This is going to give us 0.022 liters. So now that we are in liters, we can calculate how many moles we used because we had a concentration. So we had 0.1 molar NaOH. So we used 22 milliliters or 0.022 liters. So if we look, remember we converted that up top. So molarity times the volume will give us our moles. So we have our volume here. So if we just multiply this by our molarity, which is 0.1, that will give us our moles, which would be equal to 0.022 0.0022 moles. So now we have moles, and again, remember this is moles, NaOH. So we want to convert moles sodium hydroxide to moles acetic acid. Again, seems a little pointless of a step, but good to get in the habit of it. So for every 1 mole sodium hydroxide, we have 1 mole acetic acid. So guys, get in the habit of solving chemistry problems using dimensional analysis, because it's going to help you with your units. Because you guys can see here, if this wasn't 1-to-1, the position of these moles is going to be very important, because it's going to either, multiply this by 2, let's say, or divide it by 2 if this was like a 2-to-1 ratio, and a lot of people get confused where the molar ratio should be and stuff. So if you do this using dimensional analysis, you guys can see moles of sodium hydroxide cancel out with moles of sodium hydroxide. If I somehow flip this, you guys can see when I would multiply through, we would get moles sodium hydroxide squared, which we wouldn't be able to do anything with. We want it to be in moles of acetic acid. So this is just going to be 0.0022 moles acetic acid. So now we got to convert our moles of acetic acid to grams of acetic acid. So if we remember from before, moles times molecular weight will equal grams. So moles is just going to be this number again, 0.0022 times the molecular weight of acetic acid. You guys can look that up on the periodic table, but if you need real quick, it is 60.05 grams per mole. So if we multiply these two together, that will give us our grams of acetic acid. So if we do the arithmetic on this, we get 0.132. We get 0.132 grams acetic acid. So we're not done yet. We still have to get the weight percent. So if you guys remember from before, we had 2.4 grams of vinegar. So we had 0.132 grams acetic acid, 2.4 grams vinegar. We multiply this by 100. That will give us our weight percent. So if we do this out, we get 5.50%. And that would be our weight percent vinegar. So that's pretty much it for the calculations end on this lab. Again, it's a little more difficult than kind of the stuff we've done before, but once you get it, it's pretty useful to do. Titrations are a very useful tool in chemistry and stuff like that. You guys are going to be doing 2 titrations of this, so just to get a handle on it, to get accurate readings and everything else. And once you solve that on the post lab, you're going to be given a data set, and you're going to be doing some of the statistics on it, kind of like what we were doing in the first couple of labs. Should be the exact same stuff we were doing from before, so I'm not going to go over that again. If you guys have questions on that, reach out to your TA, reach out to me. We'll gladly help you through it. Other than that, that's it for this pre-lab.